Hello and welcome to this 10th lecture of this module. You know that in this module we are discussing about this multiple random variable, and it's in last couple of classes we are discussing about the functions of multiple random variable. So far we have discussed about one function of two random variables and their general cases and their application to different problems we have seen. And especially in the last class we have seen that one example on the civil engineering problem, that how one function how to determine the PDF of the functions of the random variable. So today's class basically we will be going through the if there are more than one function. So that means the known random variables are say x and y, and there are two more new functions are there, say z or w. Based on this earlier random variable x and y. So we will be interested to know that what is the joint density of these new functions, that is z and w. So now you know that whatever we have discussed earlier, that once we know their joint density, and from there we can even obtain whatever we need. For example, the marginal densities we can obtain their conditional density and all. So the focus of our today's class is to discuss about their density, or rather the joint density of two functions of the two random variables. And of course we will take this one from this 2 by 2 case to this general case, from this n numbers of variables to m numbers of new functions. So that we will generalize later. But to start with today's class, we will take one more example from this one function of out of two random variables, and we will take this problem in such a way that there are more than one roots. If you recall that couple of class before, we discussed that whenever we are having more than one root, then we have to take a summation of for all the possible roots, and that type of one example we will take, which is again the only a single function out of the two random variables. So we will start with that, and then we will go to these two functions of two random variables. So our outline is this. So one function of two random variables, we will put one example, and after that we will go to that the two functions of two random variables, and we will discuss their joint density, linear function, joint normality. This is important because when most of the cases, or many cases I should say, that there are random variables which are jointly normal, joint Gaussian distribution is observed, and if they are having two new functions, then what's their distribution properties and all. So to start with, as I was telling, that we will just take one more example of this one function of two random variables, and this example is based on the kinetic energy that is being stored in a structure during an earthquake time. So the you know that during the earthquake, generally a structure vibrates, and we can have their velocity component in two orthogonal direction, and their resultant velocity we can obtain, and we may be interested to know what is the property of that resultant kinetic energy. So based on that, we will be taking a simplified structure, and here the one storied simplified structure has been obtained, and in that structure there's the idealized case, you know that if you have the general way of analyzing this earthquake force is that we generally assume that concentrated mass at the floor level, and based on that we obtain some force at that level, and we calculate what is the kinetic energy. So here we will be taking one such problem for one idealized one story structure. So this problem statement is that a model of one story building is shown in the figure. So let us see the figure first. So this is a one storied building, and as I was telling that mass m is concentrated at its first floor level. Whose total mass m concentrated at the roof level, and when subjected to the earthquake ground shaking, the building will vibrate about its original position, inducing the velocity components u and v. So this u and v are in two orthogonal directions, of the mass with the resultant velocity. You know that if the u and v are the velocity component in two orthogonal directions, then their resultant velocity will be denoted as w, and w is equals to square root of u square plus v square. Now, if u and v are the random variable with a standard normal distribution, that is it is a normal distribution with mean 0 and standard deviation 1. So, we know that how this distribution function is. So, both of them, that is u and v, are distributed is the standard normal distribution they follow. So, so what we have to determine is that probability distribution of the resultant kinetic energy. Now, if this is the force, then we have to first know that what should be the kinetic energy, and then we will be able to determine what is its probability distribution. The information that we know, that the marginal density, that is the density of the u and v, are known to us, which is standard normal distribution. So, determine the probability distribution of the resultant kinetic energy of the mass during an earthquake. So, as we are just explained in the problem, that this is the mass that is concentrated at the first floor level, and if we just see it from the top. So, this is the component of this velocity u, and this is the component of velocity v, and their resultant is w, and which is, you know, that the square root of u square plus v square. Now, if we see that their kinetic energy, then this can be explained, this can be denoted as k, and this can be finally written that this m u square plus v square. So, basically we are having two random variable which are for which the distribution is a standard normal distribution, and we are just adding them up after squaring them. So, u and v we know. So, what is the distribution of the u square plus v square, where u and v both are standard normal distribution? That is the basic question here. So, you see that if we just now denote that a equals to m u square and b is equals to m v square. So, we can write the total resultant kinetic energy is equals to a plus b. So, now we will see what is their distribution of the a and b first. Now, this one, if we just take the specific value of those random variables, we can write that a equals to m u square. So, that u will have that plus minus square root a by m. Now, you see that here we are getting the two roots. So, we have to, whatever the distribution that we will get, we have to get it for the both these roots. And now they are we have discussed this earlier, how to get their distribution of their functions. So, we have to get their Jacobian, that is du by dA, and obviously that absolute value of this derivative. So, this is the du dA is, if we just do this derivation, it will come that 1 by 2 square root ma, and its mod, the absolute value is the positive root of this one. So, that is 1 by 2 square root ma. Now, we know that for this, if we want to know what is the distribution of this a, when we know the distribution of this u, then we have to multiply it by its Jacobian or divide by its the inverse of this one, that is dA du of this absolute value, and we have to do it for the all the roots, that is for all u. Now, here there are two roots, that as you can see, and we also know what is the distribution of this u, which is a standard normal distribution. So, if we just put this standard normal distribution in place of the distribution of u, then what we will get is this, that is f a of a is equals to that this is the first root, which is the positive of this square root a by m, and the second root is that negative of that square root, that is a by m. So, these two that is multiplied by its Jacobian 1 by 2 square root m a, and after some algebraic rearrangement, we will get that 1 by square root 2 pi m a exponential minus a by twice m for a greater than or equal to 0. So, this is the distribution of A that we got from what we know that. So, here what you have to do is that maybe one more step could have been shown here is that this is the A few of this component, means that you are putting that standard normal distribution. You know that how to what is the form of the standard normal distribution, and so it will be thus that 1 by square root of pi, because the sigma is 1, then exponential of minus half of this one, because mean is 0 and standard deviation is 1. So, if we put both these things into places with this respective this component, that one is the square root A by m and other one is this minus square root of A by m, and then if we add them, then we will get this form. And for the B also the expression is same, that is now this capital B is equals to capital B is equals to m u square m v square v square, and V is also is having the same standard normal distribution. So, from there if we want to know what is the distribution of this B, then B distribution also will be the similar one with this parameter change as B. So, it will be 1 by square root of 2 pi m B exponential minus B by twice m for B greater than or equal to 0. So, which is a chi-square distribution with 1 degree of freedom, that we know this distribution. And now, if we want to know what is the distribution for the k, and this k, you know that k equals to a plus b. So, so k equals to a plus b, and that can be rearranged, that is b equals to k minus a. And from this addition in the last class also we discussed that last class or the last to last class, that a plus b if one function, then how to get the distribution of that one. So, we are using the same thing. It can be expressed in the two different way. One is that you just explain the function in terms of only one variable, either a or b, and do this integration for the entire range for the variable that you have kept. So, here, so one such is there. So, here we have keeping that variable a here. So, this so this is the distribution of this a, and this is the distribution of the b expressed in terms of k minus a. So, now we are just eliminating out the b. So, we will do this integration for the entire range of this a. So, that's why it is 0 to k, and this it is in integration with respect to a. Now, if we do this integration, then we will get that 1 by 2 pi m exponential of minus k by 2 m integration 0 to k a power minus half k minus a power minus half dm. Now, so this integration, if we want to do, it is the closed form integration is not available, but if we just replace this a by k by r, so this a by k, then it can be expressed that this integration limit will be 0 to 1, and it will be r power minus half and 1 minus r power minus half dr. Now, this is nothing but a beta function with parameter half, and this is also half. So, beta half comma half, this is a function which also can be expressed in terms of this gamma function, and gamma function few standard values we know. So, this integration component we can get from that gamma function, which is explained here. So, this beta half is equals to this gamma half multiplied by gamma half by gamma 1. So, which is now equals to pi. You know that this gamma half is equals to square root pi. So, if we are getting this beta half is pi. So, basically, so this integration is the value of this integration is pi, and that pi and this will cancel. So, this final form of this k, that distribution of this random variable k will be your 1 by 2 m pi cancelled e power minus k by twice m. Now, you know that this is also a chi-square distribution with 2 degrees of freedom, which is nothing but the distribution of the total kinetic energy induced during the earthquake time. So, now once we know this distribution, obviously this support is k is, you know, it is forgot to mention here that this k is greater than or equal to 0. So, now once we get this support, and this will be now whatever the properties that we know, that we can obtain, and that we have discussed in the earlier classes as well. Once the distribution is known, all other properties can be assessed. So, now we will go to the two functions, as I was telling that sometimes we need to we need to know what is the there could be, it is possible to have that means two more functions out of the whatever the random variable that we are having. So, if we are now talking about more than one new random variable, so you know that these functions are also a random variable. So, if we are talking about that more than one new random variable, then we will be interested to know what is their joint density. So, and also you know that if we know the joint density, then from the joint density we can get their marginals or whatever the distribution or their properties we can assess. So, that is why so far we have discussed the one function, and here we will see one more interesting point is that sometimes even though we are looking for a single function, and it will be shown that it will be even sometimes easier to introduce a dummy function, means another new function of your own choice, and follow the procedure to obtain the joint density of the two new random variable, and then you get that marginal density of the random variable that is of interest to you. So, sometimes this procedure is found to be mathematically more easier than to get the distribution of a single function out of two random variable, that we will discuss. So, our motivation here is that we have discussed about the one function so far out of two random variables, but there it will be variables, but there may exist more than one function also. So, here we will be discuss about this two functions of two random variables, and also gradually we will take this same concept for the m functions out of n random variables. So, that will be the general case. Well, so what we are having is that two random variables is there, let that x and y be the two random variables with the joint PDF fxy xy. So, we have two random variables and their joint PDF is known to us. That means, we know whatever the properties, their marginal distribution, everything we know if we know their joint distribution. So, this joint distribution of these two random variable x and y is known. Now, there are two functions, one is that gxy and other one is hxy are used to define the new random variables. So, you know that these functions are also also a random variable only. So, suppose that we are denoting that gxy as the z and this hxy as the w. So, what we are interested is to determine the joint density or the joint PDF between this z and w, that is f z w z w expressed in terms of their lowercase letters. So, once we know this one, then you know that as we have started that the joint PDF of x and y is known, means we know their whatever the properties we need to know. Similarly, if we can obtain this joint density of their functions, then whatever we need to know we will be knowing. For example, their marginal PDFs of this z and w, that is fz expressed in terms of z and fw expressed in terms of w can also be easily determined from the theory that we have discussed earlier. So, now we are interested to know what is that the joint density of f z w from the joint density of f x y, where x y is my original random variable and z and w are the functions of this original random variable x y. Now, the determination of this joint density f z w can be done similar to the one function of two random variables. Basically, keeping the fundamental concept same, what we can express is that their cumulative density, that is f z w expressed in terms of z and w, can be expressed at that probability that this z for a specific outcome of in the sample space, it should be less than equals to z, and w should be less than equals to w. So, this comma, you know that also we discussed earlier also, this comma here indicates that the simultaneous occurrence of both these events. So, in whatever cases the both these events occur simultaneously, we will get their probability, and that probability is nothing but the cumulative probability of the joint distribution between z and w. Now, this one can be again expressed that you know that this z is a function of this g x y. So, this can be expressed in terms of g x y, which is less than or equals to z, and this can be expressed as h of x y less than or equals to w. So, basically what is expressed is that this x y, so that we are looking for a subset x y which belongs to a specific set denoted by r z w. So, this is the probability where this condition, the simultaneous occurrence of these events is satisfied. So, once we know this region, that means I have to integrate the joint density of the x and y over that region only. So, this is the integration, as there are two random variables, this is a double integration over the region of this r z w where this condition or this joint occurrence is satisfied. So, what is this region r z w? So, since the region r z w of this x y plane such that the inequalities this g x y less than or equals to z and h x y less than or equals to w, that means these two events are simultaneously satisfied. So, this simultaneously word is important here, as I was telling that both these events should be satisfied simultaneously. So, that is what it means, the joint occurrence, and then only we will get what is their joint distribution. Okay. So, this is straightforward in the sense that this is the fundamental concept where even while discussing about the one function out of two random variables, that this fundamental concept was same. Only thing is that there the resulting function was a one dimensional, means that only for the single random variable. Here we are going from one two dimensional plane to another two dimensional plane. So, so it is mapped from the one surface to the another surface. The first surface is the x y consists of this original two random variable, and the other surface that we are talking about is this z w, which is mapped from this x y through this functional dependence g x y and h x y. So, now let the two functions represented as this z equals to g x y and w equals to h x y be continuous and differentiable. So, if we just going on this with this assumption, so basically what we are talking about, these random variables are the continuous random variable, and whatever the function that we have taken, that is differentiable at every point. Now, the point z w may have many solutions for a particular point, and those multiple solutions are represented as that g x I y I is equals to z and h x I y I is equals to w. So, now for the, so it can be happen that from the surface or from the plane z w for one combination we could have multiple solution, means multiple representative point on the x y plane, and those are denoted by this x I y I. So, if that is the case, now from the concept of this probability, that we can express that the probability of z from a very small region of this delta z, that is z lying between z and z plus delta z. So, remember that this capital letter, as I was telling I told earlier also, that this capital one is the random variable and the lowercase letters are the specific values. So, this random variable z in between that z and z plus delta z and simultaneous occurrence of this w in between w plus w and w plus delta w, which can be also written as this in place of this z we can write that function g, and this w can be replaced by the function h. So, if these values are in between this small area of this delta z and this delta w, that can also be written as this function is equals to nothing but there the density, the probability density at that point means the ZW multiplied by that elemental area. Area means here we are talking about the two random variables, that's why it is area. So that the density multiplied by this small elemental area, so that will be the total probability. Now see the difference here from the single random variable to the two random variables here is a single random variable. Whenever we are discussing about the probability density multiplied by a small elemental length over the axis represented by the random variable. So that the area itself is giving you the probability. But here whenever we are taking it to the two dimensional case, that means I have to consider a volume, that is the density multiplied by the small area below that density curve. So that will give the probability. Similarly, you can even extend this one to this even for the 3 random variables, 4 random variables. So that will be some hyperplane and the hypervolume to represent that that probability. So here for the two dimensional case, there is density multiplied by the small area, which is the probability of this joint occurrence of these two event. Now to evaluate the equivalent of this this area, that is this delta z and delta z multiplied by delta w, which is the area on the plane represented by the new random variables, that is z and w. Now this area I have to find out what is the equivalent area on the xy plane, that is the original random variable. So let us consider a point A in the given figure. So here you can see that now this is the plane which is made by this z and w. So here the point that we are talking about, the A, and A is the coordinate having that z and w. Now we have considered a small elemental area surrounded by this A, B, D and C, and this AB is your delta Z and this AC is your delta W. Now we are interested to know so that some equivalent area or equivalent or the representative of the same area in this ZW plane on the XY plane. So you know that this will be obviously be distorted, and that equivalent area, if we represented this represented by this A prime, B prime, D prime and C prime, and this total area as we are talking about is a delta I, then we can express that from the figure. We can see that the point A Z W gets mapped onto the point A prime xi yi. So this A is mapped to the point A prime whose coordinates is xi yi. Okay. Now similarly other points also, means other that B prime, C prime, D prime are also will be mapped in a similar way. So thus the A prime, B prime, C prime, D prime represent equivalent parallelogram in the xy plane with the area delta I, what we have just now shown in the figure. So now the probability equation described previously can be rewritten as that the summation of all this representative area, that is if it is belong that P x y, the combination belongs to this that represented area delta I, should be the summation of for all this representative point, the xi yi multiplied by their elemental area. So this is the joint density of the xy between x and y, and this is the area over which we are interested to know how much probability is there. So we have to just multiply that area and its density. Now if we equate both the equations now from the whatever the equation that you got from here and the equation that we have represented here, so both we are referring to the same probability and express one in the ZW plane, other one is the on the XY plane. So you can equate these two as the probability that we are looking for is the same probability. So these two are now equated to get that if ZW is equals to single equal to so of this function, and so this delta Z delta W is taken here as a in the denominator. Now let that this G1 and H1 represent the inverse transformation. So inverse transformation means that we have that Z equals to Gxy. So now we are just representing it that in terms of the x we are representing in terms of the zw. Just like that we are looking for the solution for this x and y. So this is, so whatever the function through which it is represented, we are just denoting as a G1, which is nothing but the inverse function to represent the x, and similarly for the inverse function of the h is nothing but the H1. When the point a z w moves to this a prime xi yi, the other points b z plus delta z comma w moves to b prime, c z comma w plus delta w will moves to c prime, and d, I think it will be better explained from this figure directly. Is just as I was just telling that a is having the coordinate z w, this is mapped through a prime. Now what is the coordinate of this b? B coordinate is nothing but it is z plus delta z and w, and coordinate of c will be z comma w plus delta w, and coordinate of d will be z plus delta z comma w plus delta w. So these points are being mapped to this a prime, b prime, c prime and d prime. So now as these are mapped like this, I think the map will be the better word instead of this moves. It will be mapped through this point. Then what we can write, that the coordinates of the b prime can be written as this g, that is the inverse function G1 h plus delta z comma w is equals to G1 zw plus its derivative at that point multiplied by what is the change, that means the delta z. So we know this one from this fundamental theory of this calculus. So this can be again, so as you know that this is the x1 plus d G1 by dou G1 dou z multiplied by their value of the change, that is delta z. Similarly this H1 z plus delta z comma w can be represented by xi plus delta dou H1 dou z multiplied by this delta z. The coordinates of c prime will be now this one, that similarly that this is for the b prime, this is for the c prime xi plus dou G1 dou z delta w and xi plus dou H1 dou z delta w. Similarly that so that's the total area, that the area that we are talking about in this new in this xy plane is that a prime, b prime, c prime, d prime is nothing but the a prime, b prime multiplied by a prime, c prime sine of theta minus phi. So there is a kind of distortion that we are taking through this. So this a prime, b prime cos phi. So after this trigonometrical rearrangement, we can get that. So this a prime, b prime cos phi is nothing but dou G1 dou z multiplied by delta z, and similarly the other points can also be represented by this derivative, their rate of change multiplied by their amount of total small change. Okay. So this can be again this figure can be referred to basically we are what we are obtaining is that total area, total representative area that is on that plane xy. Okay. So these are the values we got, and if we just put it back to this equation, we will get what is the total area delta I, and this is exactly what is done here, and we got this form. Now what we are interested is now is that this delta I by delta z delta w. So this is the point that we got here. So this one we just want to obtain. So this expression now can be defined through this one, that is this will be cancelled, and this dou G1 which is the inverse function of this G, dou G1 dou z dou H1 dou w, dou G1 dou w, dou H1 dou z. Now this can also be expressed in terms of the determinant of the matrix of this one. So this multiplied by this minus this multiplied by this. So this is the, now this determinant, if you see, this is the Jacobian of this Jacobian represented by the ZW. Now if you recall, when we are interested to know the single function, then also we got the similar Jacobian consists of this only one element, and that one element can be seen here as this 1 by 1, this one. So dou G1 dou Z, so which was the inverse function of that one, and this determinant we used in case of this in this single random variable. Now when it is becoming that two random variables, two functions, then we are getting a 2 by 2 matrix for which the determinant is nothing but its Jacobian. Similarly, if there are three functions, then obviously if there are three functions and three random variables, this will be your 3 by 3 matrix for which the determinants needs to be evaluated, which is nothing but the Jacobian of the three random variables. So here we are just talking about two random variables. So we got that this is the Jacobian, and again from the same equation where we are just putting that is delta I divided by delta Z multiplied by delta W, that is replaced by this Jacobian now to get that closed form So this is the joint density between this ZW, which is nothing but the this joint density of this xy multiplied by its Jacobian, and it is summing up for the all the possible solution, all the possible roots, and this one obviously we have to express in terms of this z and w, that this xy, the joint density between x and y. So this is the final form if we are having the two functions out of two random variables. Now if we want to generalize, that is one-to-one transformation, so remember that what I forgot here is to mention that this is there only for when we are talking that there are some one-to-one transformation. Then what will happen? So one-to-one transformation means there will be only one root, and that one, when we are talking about that one-to-one root, so that means there is no need of this summation, that is f z w will be equals to the Jacobian multiplied by their that joint density of the original random variable expressed in terms of z and w. That is important. So here, so if let that x1, x2, xm be the multiple random variable with the continuous PDF and the continuous joint PDF, which is f of x1, x2, xm expressed in terms of x1, x2 up to xm. The PDF of the multiple random variable y1, y2 up to yn defined by the set of one-to-one transformation, say that y1 equals to g1 this gi, this is a function gi of this x1, x2, xm for I equals to 1 to m, and this is given by again from the same principle, that is this new joint density is equals to the Jacobian multiplied by the original joint density function expressed in terms of that y1, y2, yn, and that Jacobian look like this. So these are the x1, x2, x3 are the original random variable, and y1, y2 are their function, and this is a joint Jacobian, and this Jacobian has been multiplied that absolute value of that Jacobian. Now if we take the case of this discrete variable, that is where the joint density joint probabilities are determined numerically and it is concentrated at some specific point, the marginal PMF can be obtained directly, and how we do it, it will be better explained in terms of one example, and after we just discuss this example of this discrete random variable, that is through PMF. After that we will take it for the case whatever in case of the continuous random variable what we have discussed now. Now for this PMF, how we can do it, we have taken one example, and we will see that that case means the point to point basis we will just evaluate what is there, what is the distribution. So we have taken one example here, an engineer use uses two types of pile drivers, the first of which produce x1 pile a day, and the second one is an older version which can complete x2 unit during the same period of time. Mechanical conditions, site conditions, soil condition, climatic conditions, all these conditions can influence on this x1 and x2, so that this x1 and x2 are treated as the random variable. The bivariate distribution of this x1 between the x1 and x2, the joint PMF, are given in the table and which ranges from this 0 to 2. So, 0 to 2 units. So, x1 can take the values 0, 1, 2, and x2 also can take the values 0, 1, 2, and their joint PMF is shown in the next slide. What we are interested, the 3 units of the first type are obtained to be used with the available unit of the second type. Determine the marginal PMF of y to know the distribution of the random variable y equals to 3x1 plus x2. So, our function here is that 3x1 plus x2, and what is supplied is that their joint density is given here, that is when x1 equals to 0 and x2 is also equals to 0, it is 0.06, when x1 equals to 0 and x2 equals to 1, it is 0.11. Like this 3 by 3 matrix is given here, and you know this last column is the marginal of this x1 and this is the marginal of the x2, and obviously the total summation will be equals to 1. So, now to know the distribution, the marginal distribution of this y, what we can do easily, because this is only that 3 by 3 matrix only, what we can do is that we will take the specific values what the y can take. So, if x1 is 0 and x2 is 0, then the y also will be 0, and the maximum value of the y will be obtained when this x2 and x1 both are maximum, that is the x1 equals to 2 and x2 equals to 2, that means the y will be 3 into 2 plus 2, so 8. So, y can take a value from 0, 1, 2, 3 up to 8. So, this total 9 discrete values can be taken by y, and what we are interested to know, what is the probability distribution, that is the PMF for the y. And now, if we just take it by their marginal PMF of the y, just 1 by 1, that is when the y equals to 0, that means the x1 equals to 0 and x2 equals to 0, we know that their joint density is 0.6. Similarly, for the all such combination of this x1 and x2, we know what is their joint probability and we know what is the value of the y. So, when we are interested to know what is the marginal distribution of y, so these values we should see, that is y equals to 0, y equals to 1, y equals to 2 up to y equals to 8, and for this what is their probability for this, which is shown in the last column. So, this is the PMF for the y, and y can take 9 discrete values and their probabilities, corresponding probabilities are shown in the last column of this table. So, this is for the discrete case where, and this is a very small problem where we can just pick up the corresponding values directly. Now, if we take one problem which is where the random variables are continuous and we know their joint distribution, and we want to know the joint distribution of the other two random variable which are the function of this original random variable. One such example is taken through this cost benefit ratio of the project of some civil engineering project, is the benefits x and the cost y of a particular scheme are treated as to be the random variable on the account of the numerous factors considered to be unpredictable. From the trial calculations based on the past projects and the joint PDF is assumed to follow a bivariate negative exponential distribution, which is represented by this, that f x y is equals to e power minus x plus y, where this x and y both are greater than or equal to 0, and what we have to determine the density, probability density cost to benefit ratio. So, x by y. So, this one is the benefit is x and this y is the cost, their joint density is this expressed in this form, and we are interested to know what is the probability density of this benefit to cost ratio, that is x by y. Now, now see here, there are two random variables x and y, and one their joint distribution is given, and we are looking for one function here. Now, as I was telling before I start these two functions, sometimes this can also be done the way that we have done, is that if there is only one function is asked for, that whatever we have done earlier, that can be you use that theory to get what is the ratio. But we will just see through this example that if we introduce another new random variable, which may be not of our interest so far as the problem is concerned, but the problem can be solved very easily, because we will first find out their joint density, and from the joint density we will find out what is the marginal distribution. This is what is explained through this problem, is that so one function is the z equals to x by y, and the other one we have just introduced is that w equals to x plus y. So, sometimes the solution means the joint density will depend on what is the new function that we have introduced, but so far as the marginal is concerned, that marginal of this z, that will remain same. So, generally a very simple function is assumed as this function so far to make the calculation simple. So, the next step is to determine the inverse function of x and y, that is z equals to x by y. So, x equals to z y and x equals to zw minus zx, that is y equals to w minus x. So, x equals to zw into 1 plus z minus 1. Similarly, y is equals to w into 1 plus z y. So, what we have done, these are the two functions are there, and what we are doing is that we are getting the inverse function first, because we know that we have to get this inverse function to get its Jacobian. So, once we get this one, then we can calculate what is their Jacobian. Okay, this is the final form that we have to obtain, that is f zw is equals to their Jacobian multiplied by the original density. And so, this original density, when we are talking, we have to express it in terms of the z and w that I mentioned. So, this in place of the x, we are writing that zw 1 plus z inverse and w into 1 plus z inverse. So, which we are getting from this x and y here, and this is multiplied by this Jacobian, and this joint density also we know that e power minus x plus y. So, this one plus this one, which we can simplify to get that z equals to e power minus w. So, what is pending is that we just want to know what is its Jacobian, and Jacobian is, you know, that is a dou x dou z and delta x delta w, and this Jacobian, if we just solve it, we will get this form, and after doing this calculation we will get finally what we will get is that w into 1 plus z power minus 2. So, this is the Jacobian. So, that joint distribution will be its Jacobian exponential minus w. So, w into 1 plus z power minus 2 e power minus w. So, this is the joint density between z and w. Now, when we want to know what is the density of this z only, because z is the benefit to cost ratio. So, we have to calculate its marginal. Now, when we are calculating marginal, that means the other variable has to be marginal out by integrating over its entire range, which is 0 to infinity. So, when we are expressing this one here, we are supposed to write that this z comma w is should be greater their support. So, z comma w is greater than equal to 0. Okay, and I hope it was mentioned earlier. Yeah, that's for like this, that x comma y is greater than equal to 0. This is its support. Okay. So, we are just integrating out that w to get the marginal density of the z, and this is nothing but if we just do this integration, we will get the form as that 1 plus z power minus 2 for z is greater than equal to 0, and otherwise it is 0. So, this marginal density of z equals to 1 plus z power minus 2. So, this is the density of this cost to benefit the benefit to cost ratio, that is x by y. Now we will take up some special cases where that through this two functions. The first one is that linear functions only. Now linear functions means when there are we are considering, we are just multiplying it by some constant and just there we are adding them up. This is the linear function, and we will just see that for a linear function how the final form looks like. And also we will take up one thing of this joint normality. If the original distribution is joint normal distribution, then what will happen to that resulting joint distribution. So first it is a linear function. Let that z equals to ax plus by and w equals to cx plus dy, and if that AD minus BC is not equal to 0, this is one condition, because this AD, what is the coefficient of x and coefficient of y minus the multiplication of the coefficient of y and coefficient of c. If this is not equal to 0, we will see in a minute why this is one requirement. Then the linear function has one and only one solution, and the solution is that x equals to az plus bw and y equals to cz plus dw, where this capital A, B, C, D are the constant which can be expressed in terms of the lower case of this constant, the A, B, C, D, through this expression. This is just basically what we are doing, we are getting their inverse function. So once we know this inverse function, and also we know that what is the Jacobian of this x y, and this Jacobian of the x y will be, you can just express that dou x dou y, which is AD minus BC. So that's this joint density is that ZW is equals to 1 minus 1 by AD minus BC and fxy az plus bw comma cz plus dw. Remember here we are using this Jacobian of xy. You can use the Jacobian of this zw also, depending on where you are putting. This is a 1 by this Jacobian that we are doing. In the earlier example, what we did is that we just multiplied the Jacobian, and that Jacobian was between the function, that is a z and w. So based on that, where you are putting this. So now if we know these functions, so if it is a linear function, we know their coefficient, we can easily calculate what is this capital A, B, C, D, and we can express in terms of their z and w, and we will divide it by this function, this Jacobian, and that will give the joint density here. Now you see it is, as this is in the denominator, so if this is 0, then we will not get the solution, which will be infinity. So this, if this is not equal to 0, then we can get their solution at that, what is the joint density between z and w. Now the joint normality, let the random variable x and y be the jointly normal with the distribution, you know that it is mu x, sigma y and rho. So this mu x is the mean of this random variable x, mu y is the mean of the random variable y, sigma x square is the variance of the random variable x, and sigma y square is the variance of the random variable y, and rho is the correlation coefficient between x and y. There will be a comma here between mu y and sigma x square. So this is a joint normal distribution, and the functions that we are talking about, the linear function again, that ax plus by and w equals to cx plus dy. If we have this function, then we can solve it to know that what is its joint distribution. Then it can be shown that this z and w are also jointly normal, as this f z w will be exponential and the quadratic exponent in this z and w with the distribution n mu w comma mu z mu w sigma z square sigma w square rho z w. So this is the correlation between z and w, variance of w, this is variance of z, this is mean of w, this is mean of z. Obviously again one comma will be there between mu w and sigma z square. And to know that what is this mu z and mu w, if we just solve this one, we can say that this mu z is equals to a mu x plus b mu y. Similarly, means it is just, you can see that here the way we are just adding it, it is very easy to remember that this a multiplied by this mean of this, and b multiplied by the mean of this. So, this is basically you are taking the expectation of the both the side. So, this is the mean and this is the mean of this w, and this is the sigma sigma z square. The variance of this z is that you know that it is multiplied by this the square of the coefficient a square sigma x s square b square sigma y square multiplied by a factor. If they are not independent, then this 2ab rho times their product of their standard deviation. Similarly, for this sigma w square is expressed through this one, and their rho zw can also be expressed through this expression using the correlation coefficient between x and y here. So, we will take up a problem on this one maybe in the next class on this joint normality. In many cases, there are some random variables where we can say that these are jointly normally distributed, and we know there are some linear functions we have to use for some of the civil engineering problem. And if we know this expression, then we can easily get what is the joint distribution of the new random variables there. In the next class, we will take up some, as I told, some of the problems on this one, that the theory that we discussed in the last these two random variables, maybe one or two problems we have already discussed, maybe one or two problems we will take, and after that we will take you through that copula which will be used for these multiple random variables to know their joint distribution from their marginal distribution. Thank you.